Hello, everyone. Happy Tuesday. Happy Thursday. Thursday will be happy Thanksgiving. Okay, so yesterday I published 2 assignments for Thanksgiving week and the week after. Okay, so I reorganized our Canvas, the shell. So let me give you a new orientation. So make things easier, basically, for you to find out. Okay. So let me share the screen right here. Okay. Oh, this is my Geoda. Okay. All right. So you can see the first one is basically our Zoom meeting every day, every week. Okay. And then if you don't know where our Zoom meeting, the link is, it's right here. Okay. You can just click this link and you can find the past video. I need to update for the past week. Okay, then I organize all the labs, okay, into this new module called labs. Okay, so here you have your new module, analyze the relationship and spatial modeling. So basically what I did is to combine the past lab 3 and lab 4 for previous semesters into one lab, because I see this one is really good, the one I show you last Thursday, using ArcPro. Give you a full orientation on how to use their spatial analysis. I really like it. And I actually recommend to use ArcPro to do this lab, because you can see ArcGIS really, put a lot of effort into this spatial modeling business. If you use, like today I'm going to show you, if you use open source GIS, you need to switch back, between different softwares. But here in ArcPro, you can just get the job done with ArcGIS. Okay, so if you're using Mac, you don't have your ArcPro installed on your own computer, you can use Citrix. Okay, so if you don't know how to do that, please contact me. Please stay after our class and I will show you how to install Citrix receiver. But I highly recommend you use ArcPro in this lab. Okay. All right. Why I like it? Because let me zoom in a little bit. Okay. If you click on this link, you will see the instructions. And this is a roadmap. This actually is the workflow, the general workflow can be used for your own projects. Okay, so you can see the first step in this lab is to clean and explore your data. You're going to analyze your data, but if you don't know your data, what kind of attributes, the fields in your table, you don't know how to analyze it, right? So the first one guide you to clean and explore your data. Okay, and then you're going to explore the relationship between your target variable, in this case is the house price, and the contributing factors, for example, square foot of living room, right, living space, or the distance to the lakes, right? Remember last time? Yeah, so you are going to use scatter plot. Okay, scatter plot in ArcPro, which is beautiful, which is very handy tool to let you, have this platform to explore the relationship between your target variable and the contributing variable. Okay, and then you're going to build your analysis. In this lab, we are going to play with regression. Okay, you will do 2 types of regression. Number 1 is normal OLS, okay, ordinary least square regression. So just like your stats class, okay? But you will see in many cases, this OLS doesn't work well because spatial is special. Spatial is special. For one thing, in your attribute table, you don't have that distance to lake. Okay, You don't have that distance to lake. So this distance to other spatial features, in this case, the biggest lake in King County, right, actually contribute, something to your house price. Okay, and the second one is you will have this, spatial. Let me use the text. Spatial autocorrelation. Between OLS, okay, regression, residuals. Okay, so what is, let me move our chat box. What is spatial autocorrelation? That is something, some variable related to themselves, but at different location. In other words, this spatial autocorrelation is the first law of geography. Anyone can remind me what is the first law of geography? Yun? Can you help us? The first law of geography? Yes. Or James? Anyone, Ginger?
I think it is.
Okay, go ahead.
I think it is how things are related to each other.
Exactly. And if we are closer, we're close to each other, we are more related. Yes, yes, you got it. You got it. Closer things are more related. Okay, remote things less related, less similar, like our temperature, right? San Diego, Southern California is relatively warmer, okay, because we're together, we're closer compared to, for example, San Diego and San Francisco will have relatively different, more different, temperatures compare San Diego to LA because we're closer, right? And also pandemic, the COVID-19. If you live close nearby someone, get infected, your chance to get infected will be relatively higher, right? So closer things are more related. That is the first law of geography. So this spatial autocorrelation between your normal regression residuals is, well, if this, you plot out the residuals of those regression, the part, offset between your predicted value and your real value, you will see certain place this map doesn't work, this model doesn't work. Okay, so for example, let me show you here. Okay, that is this one. Okay, so you can see this one is breast cancer. We want to use, social economic backgrounds, the demographic data to explain why, certain county have certain percentage of women have breast cancer. Okay, and we apply this, just one OLS to all the counties in the United States. And we plot out the residual between predicted percentage and the real percentage. Basically, we want to evaluate how well our module, perform in each county. And we found that, here in Louisiana, this is Louisiana, right? Or Mississippi. Let me figure out. Oh, sorry, Mississippi. I have a map. You can see this map doesn't work well in Mississippi for the entire state. You can see the standardized residual is always below the mean, right? You always, let's say, underestimate the breast cancer rate in Mississippi. right? But here you can see for those, green or cyan color, you overestimate. And you can see overestimated counties and the underestimated counties spatially clustered, right? Okay, so that means, this, linear relationship, this simple idealized model actually doesn't work, very well in certain place, but in those, white counties, pretty well. Yes. So how can we solve? How can we, overcome solve this question? Well, that is a place, that is a point we introduce this GWR, geographically weighted regression. Okay, so in this lab, you're going to do another one based on your observation. Okay, you can see, oh, OLS doesn't work. Then we are going to use this GWR to do our regression. So what this GWR do is, well, for each county, you build a different model. Okay, for each county, you build a different model. So this YI is a prediction for different county. And you have this linear relationship. Okay, and those X, they are contributing factors, like our living area, like, distance to lake, or, I don't know, the square foot of yard or something. Okay, so it's different contributing variable, and those B's are your coefficient. Okay, the parameters of this model. And how you solve the question? Well, you use neighbors. Okay, here, let me change it to mouse. Okay, let me clear it. Okay. How can I clear it? Okay, so let me give you a print screen. Okay, let me clear the drawings. Let me save first. Okay, and then let me clear out the drawings. Okay, here we go. And then how you solve those model, okay, for each county, you're going to use your neighbors, because your neighbors, have more contribution to your value, because the first law of geography, right? And how you choose, how you determine who will be your neighbors, you're going to use this kernel, like your kernel density. Okay, and then if they're within this hat. Okay, so you're in, otherwise you're out, you're not my neighbors, I'm not even consider you. Okay, so like Mississippi counties, we'll just consider, maybe Louisiana, nearby counties, but we won't consider LA, the values in LA. So yeah, that is how you incorporate, you choose the neighbors, and you will going to use your neighbors, just those counties, to establish your regression model. That's basically just a very simple idea. Okay, and you can have different kernel, different methods to choose your neighbors, and you have different shape. So that is why when you're out there to use your GWR, you have this choice. What's the type of spatial kernel? Okay, yeah, so this is what it does. Okay, and then you are going to, assign different, the weights to different neighbors. Okay, so that is also what this shape, this kernel does. Okay, and then at the end of the day, you basically just have this model for each county, and then you're going to predict it. Okay, and in your lab, you will see, wow, that does a better job actually. Okay, you will have higher R square, means your model worked pretty good. Okay, and last time I shared with you the plot, right? You will see the plot evenly distributed. Okay, above the average, below the average is better than your OLS. Okay. All right, so let me pause. Basically, those are the two most challenging model. So let me pause, let people ask questions. Are we good?
I have a question.
Yes.
So
Mhm.
I remember from the previous lab that you showed us, we did put the radius number, right? How about
Mhm.
K value? The weight, do we set that value as well?
K value, what is K value?
Yeah, from your previous the
Let's see.
presentation.
I
You know,
don't.
you showed a model, right? Like each
Uh-huh.
the shape of a chrono.
K value.
The one that you just showed.
Oh, the one I just wrote. K value.
Yeah.
Kernel. You mean kernel?
Yeah, with like there are different types of a kernel, right?
Yes.
Yeah,
Like
and then
this.
you see the K value, which is the height. I mean the K, the kernel. Like how can we set the height as well? The
Oh
K
yeah,
value,
yeah,
which is
yeah, yeah. Of course, of course. Oh well, this height. Well, yes and no. This height
okay.
represents the weight of your neighbors.
Mm-hmm.
Okay, so this K you can see is K brackets. That means it's a function. Okay, and this K, the value will vary like this bell shape in this case. Okay, so you can see, let me draw. For example, this neighbor, this dot, the weight will be here. Okay, and you can see this one is maybe, let's see, let's say you have another one, another neighbor here. This neighbor, the weight will be here, higher. Why is higher? Because the distance, this h, is closer. So basically this k, this function, is a function of h. So how close your neighbor is to you, to your location. And you can see yourself, this height is 1. It's 1 unit. What kind of unit whatever unit you choose.
I see. Then for all different like other types of the kernel, like the maximum is always 1, right? And
Yes,
then
yes.
depending
Well,
on the value within the radius, it just calculates its own.
exactly. Exactly.
Thank you.
So you can see this uniform basically is everyone as long as within my buffer is 1. Right? Okay, and this bell shape, this Gaussian shape, basically you have this normal distribution. Okay, and you can see this one, well, that means your weight will decrease very fast as soon as you walk a little bit far away from me. Right? Okay, maybe like 1 meter, okay, away from me, you're okay, but like 2 meters will be immediately 0. And here you have this linear decreasing the relationship. Usually we will just use this one, normal distribution. Okay, and this one, well, for geologists, this one, let me give you a real world meaning, maybe different the rock types, right? For example, this sedimentary rock within my neighbor, I will say they contributing to me, right? But outside this zone, they're, metamorphic rock or, granite. It's not the, the ideal rock type. So I will consider the contribution is 0. Make sense? Okay.
Yep.
All right, so you can see this is 2 different type of model, okay? All right, so clear. All right, so let me go to our folder. show in folder. Okay. Oops. All right. Okay, show in folder right here. Continue. Okay. Oh, why is like this? Okay, so click this. Added it. Okay. Zoom out. Oh, no. Okay, anyways, let's go back to the lab. Okay, so you can see here another thing, you can do many types of model and you can compare your model. Okay, compare the performance. Okay, all right, so this basically is this lab. Okay, so follow the steps and you will see. And here, let me make another notes. Here, you're still seeing my screen, right? Okay, all right, so you just need to finish the first one, second one, third one, fourth, and the first part of this model spatially varying relationships. Okay, so you don't need to just stop at geographically weighted regression. You don't have to do forest-based classification and regression. Okay, random forest, you don't have to do this. Okay, so basically stop here. Use GWR and rate variable and here. Okay, stop here before this part. You don't have to do the rest of the lab. Okay, so basically give you an orientation how to do spatial modeling using ArcPro. Okay, and for the submission, you don't have to produce any maps. You just need to download this worksheet. Okay, and I think I have 8 questions over there. Let's see. Okay. All right. Okay, so you can see basically I guide you when you follow the instructions. I want you to think. Don't just click on the buttons and you finish the lab. You feel I learned nothing. Okay, and then I want you to each part I give you 1 or 2 questions. Okay, for you to think. For example, the first part you're going to do the scatter plot using ArcPro, and I want you to interpret what are the top 2 property characteristics that have strong relationship to price. Okay, and then you just answer that here. Okay, and when you finish, you just need to submit this question, this worksheet. All right. Okay. All right. Any questions for this lab? Nope. Okay. All right. Then the last thing for this lab is if you want to try QGIS and GeoDA, here is how to do this. Okay. So, oh, I need to share the data with you. Sorry, I forgot. Okay, so let me share the data with you. And what you download basically is what I demonstrated last week. Okay, and you will see this is a shapefile basically. I help you convert the data already. And the first one is to do the scatter plot. You're going to use this one, scatter plot matrix. Okay, and here you can include your data like last time I demonstrated. Okay, to see the relationship. And then the next step basically is to do this regression. So where's the regression in GODA? Well, it's right here, okay, regression, okay? But here, this regression is, not that intuitive, okay? So, well, here is okay. So your dependent variable will be price, okay? And based on your explore in scatter plot, you will see, oh, let me just include this square foot of living, okay? And then that's your covariates, okay? And then how can I, choose the, OLS or GWR, okay? So if you just click on this classic and no weights files, this one is OLS. Okay, what it does just OLS, and you can, click on those checkbox and to see the testing results as you see in ArcPro. Okay, but if you, before you do this, you go to this weights manager and choose to create a new weight file. Okay, so for example, you're going to use ID, I think. There's an ID somewhere. Oh, I need to create an ID, sorry. Add ID variable here. Okay, poly ID and add variable, okay? And then you can choose queen, you can choose rook, okay? And then to, calculate the distance, okay? When you have that distance, okay? And when you click on the regression, you check this box. Okay, you click on this one to specify the weights, the weight file here, living. Okay, check this box and you're going to specify this weight file. And then in that case, you're going to select this spatial lag. Okay, spatial lag. Then in that case, you will perform geographically weighted regression. But warning here, this geographically weighted regression is a little bit different compared to the kernel method in ArcPro. Okay, so this one basically is using the continuity to define your spatial, your neighbor's weights. It's different. Okay, and then of course you will build a different model, but it's still worth to do this to compare a different model. Okay. But this is how you do geographically weighted regression, okay? And then, for example, let me just use classic, okay? And let me show you very quickly what is produced, okay? So I don't want to use weights, okay? I will just hit run, okay? And you will see those are the evaluation. You can see your R square is exactly the same one as what you see in ArcPro. Okay, and here is your variable, okay, your constant and the slope of square foot of living. So those coefficient basically is this. Let me annotate your model. So will be your price, your predicted price will equals to, let me use the text here. Okay, this coefficient for the constant is minus 43603.4, okay, plus the slope to 80.629 times your square foot of living room, okay, and plus an error or residual. Okay, let me put it as residual. All right, does that make sense, guys? Okay, and then you can see this residual. Let me go here. Okay, let me make it larger. Okay, your residual is here. You can see I have this many points. A lot of points. You have this table down there, okay? And then you have your predicted value. That is when you plug in square foot living for each point, you will predict this value. but the residual is this one. Okay, your residual is this one. And you can test your model is significant, reliable or not reliable, right? You're confident or not confident about your model. Well, you will see this probability. You can see this is 0, right? So that means it's very small chance you made mistake. In other words, you're very confident about your model. Okay, so if you want to save this result, okay, if you want to save this result, you can go here, you can save to table. That will save to a CSV file, but I would recommend save to file. Okay, save to file right here. And then, save to table, sorry. Let me roll back. Save to file is to save that as a TXT, or you can change that to CSV. Okay, save to table is just directly, right into your attribute table. Okay, so you can see here, I think I saved it one already. Let me give you another copy, number 2. Okay, number 2. Okay, residual OLS, residual number 2, and click OK. Let me close this. You can visualize it. Let me clear all the drawings. You can visualize the guys. How to do that? Well, here, when you have this map, you can click on this one. Not this map, sorry. Click on this one. Where it is? This one. Maps and rates. Maps and rates on the main menu. Okay. And then you will choose, for example, quantile, for example, percentage. Okay. Or natural break, different, classification method. Okay. Let me just use this this quantile, like 5 classes, okay? And I will choose my residual, okay? My residual, you can see, okay, all right. So you can see this is your residual map. So how well your prediction is, okay? So you can see, wow, close to the lake, I have high residual, okay? Away from the lake, southern part of this county, I have relatively also large residual, but under predicted, right? And you can explore using, GeoDA. Okay? All right, so that basically is how you do this with GeoDA. QGIS also have an option. QGIS have a model called the QGIS. Here we go. It's not grass. It's it's on my lips. I'm too excited. I forgot the name. But it's there. Let me see. Here. Hello. Come on. Okay, here we go. Okay, lab 4. Okay, see, I do the same thing. Okay, but your processing tool will be GWR. Okay, oh, Saga, sorry, Saga GIS, you will have this GWR for multiple predictor layers. Okay, and you click on this one, it will give you this, the dialog, and you just fill that out. Okay, so that is, you can see open source software, you need to switch back and forth, and you also need to do a little bit, the file conversion, save that as shapefile, and that will work well. Okay, but I still highly recommend you use ArcPro, which did a very good job to incorporate everything just into one software. Okay. All right, so let me pause for questions. Good. All right. Okay. Wonderful. So basically, this part. Yes. Yes. Okay. This part basically is to share with you the modeling. Okay. So we started last week. So this week is relatively easy. OLS. Okay. And when you plot the residual, you see this spatial autocorrelation of residual, means certain place doesn't work well. Okay, you need to build a different model. So this is the place you want to use, the case, the scenarios you want to use GWR. Okay, and then for GWR, the basic concepts. Okay. All right. Okay. So enjoy this lab. Enjoy this lab. It will give you a full, orientation on how to do spatial modeling. Okay. All right. Okay. So then the rest of the spatial modeling is very simple. It's very simple. Okay. So you can see, let me go to our lab, go to our canvas. Okay. This is the lab. And also I organize all the quiz here. Okay. So this is our last quiz, I will say. Okay. Spatial relationship and spatial modeling is our last quiz. I combine the two together. Usually I will have 4 quiz for you guys. Okay. And then if you, know how to prepare for this quiz, okay, go to our week 3. Okay, week 3, the module, week 13, sorry, week 13, the module, and you have my presentation, and I want you to pay attention to this study guide. Okay, this page. So basically, I know this Thanksgiving week and also close to the end of the semester is very stressful. So I won't give you more readings. Okay, just a few videos for you to watch. Okay, for each model, for each modeling method, you just need to be able to answer those 3 questions. Okay, what it is, how it works, and most importantly, guys, I don't want you to physically memorize things, okay? But you need to know how to use it. So what type of spatial questions can be answered by the model, okay? In other words, applications, okay? Applications. So you can see this is for cartographic modeling, okay? And this one is OLS, you know that already, okay? And this is GWR, okay? And then spatial interpolation, okay? So when you can answer those 3 questions for each type of the modeling method, you're ready to take the quiz. But be prepared, you won't see any question asking you for the, definition. What is GWR? You will see a lot of questions. In which scenario you use GWR, the application. Okay, so really understand it. Okay, you will have multiple choice. Okay, and maybe one short answer, I forgot. All right, so this is how to study this module. Okay, all right, okay. So then let me give you a quick presentation on cartographic modeling and interpolation. Okay. So what is cartographic modeling? Here I give you a mouthful definition. But long story short, just one word: overlay. Okay, overlay. So cartographic modeling will address the questions like this: where are the suitable places to build a new solar plant? Okay, where are the habitats for California lizard? Okay, where are the communities with high vulnerability to epidemic or pandemic? Okay, Or where are the next place to help Brian build his, seaweed farmland in the ocean? Okay, so this cartographic modeling is very, very useful. I like that, Brian. How you bring that out? Okay, so we'll basically answer the question, suitability analysis. Okay, let me put it here. Oh, annotate. Suitability analysis. Okay, well, can be Brian's seaweed farm, or it can be the next Starbucks, the coffee shop, right? You're going to analyze the background information and you overlay them together, right? So this can be your project, okay? So this is cartographic modeling, basically spatial overlay. You will have two approaches to, to build this model. One is just use vector data, polygons, lines, and the points, okay? You overlay everything together. In the other case is you just use raster, okay? For example, you use elevation, slope, precipitation, temperature to choose the suitable lands for alfalfa. For example, that is Violet. I think she's very interested in those the water crisis in California and how that affect our farmland. Okay, so yeah, so cartographic modeling is very, very useful actually. Okay. All right. Okay. Any questions? All right, so let me give you some example. This is an example I did when I was in medicine. Okay, my first cartographic modeling. It's very simple. So my project question with my students, I was a TA out there. Our project question is, where are the potential sites for constructing a small lab and office building given the following requirements? So you're going to find your land, your potential land for this building, but you need to meet certain requirements, right? Okay, so the requirement is this. The land use should be brushland. Okay, must be brushland. The suitability of soil, you have this evaluation from our soil science department. Okay, the soil suitability should be 2, or if I want to plant something, the hard zone, produced by USDA should be 7, for example. Okay, the hard zone. Okay, and then distance to existing sewer lines should be smaller than 300 meters. Okay, and then distance to stream should be larger than 20 meters. Okay, and the area should be, the size of this land should be 2,000 square meters, larger than that. Okay, so you can see, well, I need to prepare for 1, 2, 3, 4, 5 layers, and then I overlay them together, right? Okay, so I don't have this, the distance to existing sewer lines, but I can build a buffer. Same thing like these streams, I can build a buffer. I can use very simple spatial analysis like erase, like clip, to cut my land out, and then I will overlay them together. Okay, let me show you the flow chart. Okay, this is a separate flow chart on our, the lecture presentation. So you can see it's here. It's under spatial modeling. Okay, this is my main spatial modeling presentation, and you can see this is the vector approach for this cartographic modeling. Okay, and down here you have your raster approach. Okay, and then here this is your vector approach is here. Okay, so you can see I basically have those models. Okay, those maps. Okay, based on this map, I first need to generate suitable soils. This one will be select by attributes, right? Suitable soil should be 2 equals to 2, right? And land use map equals to brushland. Okay, and sewer line map. Okay, I use these sewer lines, the lines to generate a buffer. Okay, and then streamlines I will outside the buffer, right? Then I just intersect everything, overlay everything together, and then I will just generate the potential sites. It's pretty straightforward, right? Okay, so this is basic idea. Okay, and then you can see basically here is what I did. Okay, so for each map, you need to perform some basic spatial analysis to generate these layers. Okay, and where it's located in your toolbox, and then you just overlay them together. Okay, and then at the end of the day, erase, dissolve. Okay, you will have this flow chart. Okay, and voila, you have this map. You have those potential sites. Okay, 1, 2, 3, 4, all the way to 14 sites, and you can choose from. Okay, you can also do this. You can also do this with raster analysis. Oh, I need to skip this one. You don't need to do this. Okay, you can also first convert, your polygons into those layers. Okay, into those layers, and then you overlay the layers based on the value of pixels. Right? Okay, let me give you those, the steps. So for example, this land use type, you can convert it to a land use type, but raster data. For each raster the cell, you will have a code. What is that, the land cover in that cell? It's brushland, or it's urban, it's water, you have different values, right? For soils, you have 1, 2, 3, 4, 5 evaluation of the soil. For that cell, you have suitable soil or not suitable soil, right? For sewer lines or streams, you have, yes, this pixel is stream or not stream, 0. Okay, and then you can see here, I highlighted, you need to keep using the same cell size. Otherwise, you won't be able to, exactly match different locations. So you need to do resampling, okay? So this is the raster approach. I see a question in the chat. Yes, Brian, that's your project. Very useful for this one, okay? Yes, and then you can see you overlay them together. Okay, distance is how you calculate distance using rasters. Okay, and then the spatial overlay actually is very, very straightforward. Okay, so this is your flow chart, and then you just combine different layers. Okay, you can choose either way. Okay, yeah. So you can see in the raster approach, at the beginning, you need to do a lot of work because you need to convert each map to rasters with the same cell size. And then you need to evaluate the suitability. Okay? And then you need to calculate a buffer, blah, blah, blah. But the overlay is very simple because you have the same, raster cell size. Okay? And vector approach is relatively straightforward, easy to understand, but you need to know what kind of spatial tool you're going to use, right? Like it's a buffer, or it's clip, or it's intersect, right? Okay, so this basically is spatial overlay. That is your cartographic modeling. Any questions?
In this one, do you have to score every kind of, like, do you have to give the pixels your own values and then you
Yes.
sum them?
Yes, yes. So you can see
Okay.
here, I basically skip this part. You can see you need to do a classification. Okay, for the streams, I generate this buffer. Okay, within the buffer, it's 0. Okay, outside, the further you are, the better. And you can give them 1 all the way to 3.
I was wondering if you could also like multiply, because if you said like this is binary, you're within the buffer of the stream, that's a no-go. We just want to multiply that by 0. So you can create your own, okay, you can create your own like method of okay.
Exactly. You can also, like Professor James, that's a wonderful question. You can have your own overlay method. You can just, for this stream suitability, outside stream, well, outside your buffer will be 1, inside will be 0. Then when you overlay, you basically multiply. Within it, you multiply by 0, that is 0, totally not suitable. Outside is totally suitable. So you have this black and white, the cut. But what I did here is like a fuzzy, buffer, as far the further you are, the better. So yeah, you can totally generate your spatial overlay. Okay, and for this raster, you're going to use cell statistics, or another name is called map algebra. Okay, map algebra. So on our study guide, you will see that professor demonstrate how to use map algebra to overlay the rasters. Okay, yeah, since we don't have Thursday this week, so I provide a few videos to show you how to do that with ArcPro and QGIS. Any questions? Okay, wonderful, wonderful. You can use that, you can choose either way, okay? All right, so, oh. No. Okay, close this, okay. And the next one is the spatial interpolation, okay? But this one is also very, very simple. Let me share the screen. Okay, I see Hunter is here. Hunter, could you stay after class? We can talk?
Yeah.
Okay, yeah, don't worry, okay? Hunter is worrying about his project, so. But I bet I believe he will produce another beautiful map for us, like the first time. Okay, all right, so spatial interpolation, again, the first law of geography. Okay, so what is spatial interpolation? You can see, well, for those continuous surface, for example, our elevation, like this terrain, right? How do we know? When you use your Google map, when you switch to the topographic view, you will see the elevation rasters, right? How do you know the value for each pixel? You cannot, it's just not feasible for you to get the value, measure the value for each pixel, right? You cannot do that. The method we use is to guess, believe it or not. It's very simple. So based on your known sample locations, okay, you can have your tripod to measure those locations, the elevation, And then for this unknown location, you just guess it. Okay, how you guess? You cannot just, randomly guess the value. You will use the first law of geography. Okay, the closer they are, the similar they are. In this case, elevation. Okay, so this method, we call that spatial interpolation. You know interpolation, you guess the value in between, but this one is done over geographic space, so we call that spatial interpolation. Okay, this process will commonly used in raster data, but can also be used in vector data. For example, this polygon, guys, you can see. I know this field, for example, this our state park number 1, okay, is 100 deers. Okay, and this state park we have 10 deers. And how about this one? We don't know. Can we guess? Right? Even we have those, man-made, the boundaries between different park, but our deers, they don't recognize, they don't respect those boundaries, right? They will cross. So you can assume, okay, since we are close to those two parks, okay, maybe we can guess a value based on the similarity, based on the distance between those, parks, right? Okay, maybe the conditions in this park is similar to this one. Then I will guess, well, this park will have a higher weight. Okay, I will guess, okay, this one may have 80 deers. Okay, because they're similar. Okay, and here, well, this one is 10 deers, but I won't guess it's 10 because this one is smaller and this one is relatively larger. This is called spatial interpolation. You based on how similar those polygons are. Okay. All right. Okay. So this also related to our spatial regression. Okay. For example, in Mississippi, right? You have similar demographic, the backgrounds, the information, and those counties, they're similar. Then you can use spatial interpolation to, choose to estimate the breast cancer rate for certain unknown location, right? Okay, for LA, certain neighborhood have very high diabetes rate, okay, obesity rate, and that because they have, low income community, they're very close to those, fast food restaurant, okay, and many other factors. And then you will estimate, oh, that county, I don't have the value, but I can estimate. Okay, so this is also called spatial interpolation. Okay, get the basic idea? Okay, so closer things are more similar, and they have similar attributes, can also be similar. Okay, all right. Okay, so there are many methods to do this spatial interpolation. Okay, for example, this one is called Tyson polygon. Tyson polygon. So you can see you start with those measurements. Okay, and at the end of the day, you basically run this model. It will, dissect the entire study area. For example, this LA County, okay, into those sections. Okay, and this method, this algorithm will guarantee the points within each sector, each section. Okay, your measurement is the closest known location. Okay, and you can just use the value for that one. Okay, so for example, I just know, oh, in this location, I have the temperature is 100 degrees. Oh, that's very hot, right? Okay, and then you can guess within this entire area, my temperature is 100 degrees. because this station is the closest station. You can measure it. This part, this unknown location to this one, to this one, to this one, and to this one, they all, you know, longer than this one. This is the closest station. Okay, this method is also very, very useful. Okay, it's not for, you know, spatial interpolation. It's to, you know, divide the service area, okay, for each service point. Okay, so for example, okay, we have, you know, the testing sites in LA County. Okay, and you will, you know, guide people to go to your closest, you know, testing station to get the, you know, COVID-19 test. You don't want people to travel long, you know, travel long distance to, you know, get the test. That will, you know, help the transmission of the COVID-19, right? Okay, then you can run this Tyson polygon. Okay, then in that case, I will guarantee, oh, for this testing station, all the location within this station, all the location within this area, this will be the closest one. Sounds very interesting, right? Or Starbucks, right? Okay, where I need to, you know, have a new Starbucks, the coffee shop. Okay, this area, I have this Starbucks. Okay, they are good. Okay, and this part, they're good. Okay, oh, this one, I don't have this one. Okay, maybe this is the location you want to have a new Starbucks. Service area. Okay. All right, so this is the Tyson polygon. Any questions? You don't have to worry about those, you know, intermediate steps. Okay, they will just guarantee your segmentation here, can guarantee those locations. These points is the closest measurement. All right, okay, all right, okay, very good. And this IDW one is very similar to our kernel. Okay, so basically this inverse distance weighted method is to use this one. This basically is your weight. Okay, this D is your weight for your neighbors. Okay, so you can see here. This P, I don't know the value, what the value is, but I have the measurements. Okay, I have the measurements right here. I can measure the distance between this P, this point, with all the measurements, and this distance will be this DI. You can see that's inversed value, right? So the closer you are, the weight, the higher the weight is of this neighbor. Okay, so for example, you can see for this one to 230, the distance is 23. So the weight, I will put it as 23. You have this one, 1 over 23. Okay, times 230. Okay, and for this one, I will have this 58, but inverse over, and times 320. Okay, and for this one, I will just do another one. Okay, for this one will be 35. Okay, 1 times 580. Okay, and then you can hear, well, we have a small issue here, because this one totally changed the magnitude of your measurement, right? Okay, you don't want to just directly use your distance. You want to normalize that to 0 and 1, the contribution percentage compared to other neighbors. So that is why at the bottom, when you have this sum, okay, you want to normalize all the weights. So here you have this sum. Okay, you will have this 35 over 1. This is the weight, the absolute weight for this point. Okay, plus 58. 1, this is the absolute weight, but when you divide by the total sum of your weight, that will be a normalized to 0 and 1, right? Okay, and this one is 23. 1. Okay, in this case, you can see, let me change another color. This part will just be the relatively weight for this point, right? For example, that is, I don't know, 40%, okay, contribution from this point, okay? And this one here, this part will be the contribution, the weight for your second point. You can see maybe 60%, okay? And for this one is some percentage. Okay, so basically that is a value between 0 and 1. And then when you calculate everything together, you will have a relatively, reasonable estimation. You won't, way off because of the distance, the measurement. Okay, does that make sense? Okay, so you can also justify, adjust the power here. You can have number 2. That means you will have this P as 2, then you will have this fast decrease. Okay, it's just like our, kernel density or kernel, the geographically weighted regression. You have this type of shape. Okay, or you have this 0. 0 means you have this cap. Okay, like this. Okay, in or out. Right? Or you have this 1, it's like this, triangle shape. But it just, control how fast your weight decreasing as you go further and further away. Okay? This some not just technical details. When you're out there to use your tool, you will have this choice. But usually we will keep it as 1. Okay, keep it as 1. Any questions? Okay, the theory behind it is still first law of geography. First law of geography. All right, okay, you don't have to worry about this kriging. Okay, this basically is a more statistical method. Okay, I regret to include this one to you in this class because it's can be put it as advanced. Okay, this single method. Where's my book? Oh, here we go. I have this book just on this method. Okay, I think it's way too complicated. Let me find a video for you. Okay, for this method. You won't see any questions on kriging. Okay, maybe that is for your grad school or the bachelor program. You can study this method. Okay, but again, it is the first law of geography, guys. All right, okay, so I think that's it. That's it for this class and also the last class meeting before Thanksgiving. Okay, so again, during Thanksgiving, you just need to, well, I postponed our project proposal because last night I checked it, only 3 of you submitted. Maybe you need more time to think about it. By the way, tomorrow I have the full day, I'm just free. Okay, give me 1 hour in the morning, I can swim from, from 9 to 10, I guess. Yes, and then the rest of the day, I will be free. Okay, so shoot me emails if you want to meet tomorrow to discuss your projects. Okay, and for folks have had a meeting with me, you can see that through the discussion, we can have a, a clear picture. Okay, don't feel, you have to be very clear what you want to do in your, for your project. Through discussion, I also don't know, right? Through discussion, we can get the picture clear and clear. All right, okay, so let me stop recording, stop share, stop recording, okay? So again, if you want to see me tomorrow, shoot me emails. Otherwise, happy Thanksgiving. I will see you after Thanksgiving. We will start our new journey to explore the fancy stuff in current GIS, this field, including, the Jupyter notebook from ArcPro, ArcGIS, okay, the Python, and also Google Earth Engine. Okay, many fancy things, but we won't have any quiz. We won't have any, maybe one more lab, okay, one more lab to give you a practical experience. Okay, all right, so let me stop recording.